it's just there's some useful things there. So in the group homomorphisms, what we did give a good discussion of was the first of these isomorphism theorems. And this centered around this commutative diagram here. So the first isomorphism theorem, this applies in this situation where you've got any homomorphism psi here from one group G to another group H. So in general, if psi is a homomorphism, it might not be injective and it might not be surjective onto H. But the question is, so we know we proved some of the basic properties about homomorphisms. We proved that if you take any subgroup in G and map it over into H, the image of it over in H will be a subgroup. So in particular, if you look at the image of all of G, if you look at the psi of all of G, that's potentially a smaller subset of H, but that will be a subgroup of H. So the image of all of G over here in H will be a subgroup of H. If psi is surjective, then it will be all of H. But if psi is not surjective, then it will be some strictly smaller subset of H. And then what this first isomorphism theorem is doing is it's capturing this group, psi of G, over in H. It's capturing the isomorphism class of that group. And it's constructing a group out of G using this factor operation, constructing a group out of G that will be isomorphic to the image psi of G. Okay? So the particular factor group we use is factoring out by the kernel of the homomorphism. Okay? And this map phi is a very natural map. You're mapping any element G to the coset corresponding to little g. Okay, so that's a very natural map in that direction. And this map, eta, is very natural as well. You're mapping any coset. So any coset is, you can think of it as a little g times k. You're mapping that coset to the element psi of g, in psi of little g, which will be inside H. So we talked through the definitions of those maps last time and we discussed this result. The main work in the proof there's nothing too complicated. It's just ironing out the details, proving that this map phi, this natural map mapping any elements to the coset represented, to the coset corresponding to that element, proving that that's a homomorphism. Then proving that this map eta is in fact well defined, so that if you choose two different representatives of the same coset here, that sending it, then that eta actually gives the same image of those two representatives. So proving that eta is well defined, and then proving that eta is a isomorphism, and proving that it's injective, and there, so if you just look at proving that it's isomorphic onto the image psi of G, that is a subgroup. So that's an interesting theorem that ties together, isomorphisms, homomorphisms, kernels, and factor groups, all in this nice commutative diagram here. But the main idea behind it is any homomorphism maps a group into some kind of a homomorphic image of that, a potentially smaller subgroup of the codomain. And that image, psi of G, will be in some senses a simplified version of G, okay? Because psi might not be injective. It might collapse different elements of G down onto the same image across there, so you're losing information. So the group psi of G will be a somewhat simpler group, but you can capture an isomorphic representative or an equivalent isomorphic group using this factor group construction. So that's the first isomorphism theorem. So there are two other ones, and also another result called the correspondence theorem. Establishing these other theorems, again, it's very similar work in the proof. I'm not going to talk through the proofs in detail, but just very similar matters of if there are maps involved, proving that those are well defined, and then any issues about subgroups and normal subgroups, proving that subgroups are subgroups and claimed normal subgroups are normal subgroups, just turns on the fact that you're building them out of other subgroups or other related normal subgroups. So the second isomorphism theorem talks about a situation where you've got a normal subgroup N of G, and H being just any other subgroup, okay? So G is our containing group, N is a normal subgroup of G, and H is just any other subgroup. Then we're bundling up a couple of results here. In particular, when you look at the intersection of H and N, so the intersection of a general subgroup with this one fixed normal subgroup, that intersection, okay, we already know that that intersection is a subgroup. We proved back in the subgroups chapter that the intersection of two subgroups is again a subgroup. But much more than that, it's actually a normal subgroup of H. So not necessarily of G, because remember, being normal means that your left cosets are equal to your right cosets. But here we're only claiming that this intersection is a normal subgroup of H. So only when you take left and right cosets of this intersection, but only generated by elements of H. Okay, and again that would be a normal subgroup of H. Those left and right cosets of H intersection N associated to elements of H, they're always going to be the same. Left and right cosets are always going to be the same. So that means if H intersection N is a normal subgroup of H, it means this factor group is a valid construction, factoring H by H intersection N, okay, because H intersection N would be a normal subgroup of H. So this is a legitimate factor group to form. On the right-hand side, though, so the second isomorphism theorem is saying that this group is isomorphic to this, okay, closely associated factor group. Here, what we're doing is, okay, we're factoring out by N, but now we're not factoring G by N, but we're factoring this construction Hn. So what is Hn? Well, Hn is the product of the sets, capital H and capital N. So Hn just consists of every product, little h times a little n, okay, where little h comes from H, little n comes from N. Okay, so it's the product of two groups. And what you're establishing here is that Hn is a subgroup of G. It is a subgroup of G. I'd better make some extra comments about this because there's a few extra things to say about it, which aren't necessarily captured there just in the statement of it. So for the second isomorphism theorem, this turned on. Here we go. So for the second isomorphism theorem, so this construction, you're multiplying together two subsets, that just consists of all the products H times N, where little h comes from H and little n comes from N. Okay. So what you establish in the second isomorphism theorem is that Hn is a subgroup of G. And in fact, also to note about it is that H is contained in Hn. So how do you know that H is contained in Hn? Well, you see, this little n can always be chosen as the identity element, okay? Because n is a subgroup. So a valid choice for the little n here would be the identity element from G. So certainly this contains all the products H times the identity. So it contains every element little h from H. And also, by the same argument, n is also contained in H times n. Because the choice of the identity, that's a valid choice for this element little h, isn't it? Okay. So capital H times capital N contains all the products, the identity times every little n from n. So in particular, n is a subset. And in fact, and this is probably established, or this might be commented on in the proof there, Hn is the smallest subgroup of G containing both H and N as subsets. Subgroups, really. Okay. So this construction H times N, it gives you the minimal thing, the minimal subgroup that will contain H and contain N. Okay. And now, in general, when you do this construction in general, if you take one subgroup multiplied by another one, in general, that won't be another subgroup, okay? Because there'll be a problem caused by, about the closure, especially if they aren't abelian. Then when you multiply together two products like this times another one, it won't necessarily be able to get it back into that form. So in the case where the group is non-abelian, it won't always be true that when you multiply any old two subsets together, any old two subgroups, that you get another subgroup. But in the case where one of them is normal, the fact that capital N is normal, you'll see when you look through the details of the proof of that, is that allows you to prove that H times N is a subgroup of G. So just a few remarks there. So Hn is a subgroup of G. It contains the normal group N. So in particular, N will be a normal subgroup of this subgroup, H times N. So it will be a legitimate construction to form that quotient group, Hn factored out by N. And so the second isomorphism theorem is just establishing that isomorphism. Okay? Now, it's not saying that the two groups are the same, because in general, they might be different, because the elements here are cosets of capital N, whereas here there'll be cosets of H intersection capital N. And in general, that's going to be a smaller subgroup. You know, if H doesn't contain all of N, then H intersection N will be some smaller part of N. Okay? So the elements here will be quite different to the elements over here, cosets of a different set here on both sides. Okay? Moving on, looking at the other results established, there's the correspondence theorem. And this looks, okay, so the setting for this is a general factor group, G mod N. And what this, okay, so we already have this idea that the factor group G mod N is some kind of a simplified form of the original group G. It's what happens to the original group G when you take all the elements in the subgroup and consider them as the identity element. And look at all the consequences of that if you want to keep the thing being a group. Then the group you end up constructing is this factor group G mod N. The correspondence theorem is telling you how to think about subgroups of this new group. How are subgroups of this new group related to subgroups of the original group G? Okay. So G mod N is a simplified form of G. Is there any way we can think about the subgroups of this new group as being in some sense simplifications of subgroups of the original group G? And this correspondence theorem indeed sets that up and describes it exactly. So this mapping here, H to H mod N, so what is that? There you're considering all the subgroups H that contain N. Well, if the subgroup H contains the normal subgroup N, N will be a normal subgroup of H. And so this factor group will be a valid construction. But this factor group will be a subset of this group here, because this factor group consists of cosets of N. Yeah, those are the elements in the factor group. Well, G mod N consists of every possible coset of N. Okay, so in general, this construction here, where you take a subgroup H of G containing N, look at this factor group here. This contains some of the cosets of N. So this will be certainly a subset of G mod N, but actually, it turns out it'll be a subgroup. subgroup of G mod n. And this correspondence is exactly, so every subgroup of G mod n comes about from some subgroup of G containing n under this mapping. Okay, so every subgroup of the quotient group is a quotient of a subgroup of the original group by the same normal subgroup n. Okay, so again, this really nice mapping of, you know, all the kind of group theory stuff maps across nicely. G mod n is your simplified view of G, and the subgroups of G mod n themselves come from simplifying subgroups of the original group G that contain n. And then there's this extra correspondence, which is really nice, that the normal subgroups of this, so it's quite a hierarchy of constructions, normal subgroups of the factor group come about under this association from subgroups H that are normal in G. Okay. But it's just so that everything maps around really nicely. And then finally, before we get to some of the exercises, then we have the third isomorphism theorem. So this third isomorphism theorem relates to when you're doing kind of consecutive factor groups, so consecutive quotients. And so which is the smaller one? Here, yeah, so here you have a normal subgroup, so which is contained in, so n is the smallest. Okay, so you've got a group G, and you've got normal subgroups n and h. So you've got n and h. These are both normal subgroups of group G. So then, if these are both normal subgroups of G, in addition, of course, n is a normal subgroup of H. So in particular, valid quotients you'll be able to do would be G mod n. Valid factor groups you'll be able to form would be G factored by n, H factored by n, and G factored by H as well. And that's exactly what we're saying here. So the third isomorphism theorem says that when you factor out G by H, so this will be quite a simplified, see, the factor group G mod n will be a certain simplification of G, considering all the elements of the normal subgroup n to be trivial. The factor group G mod H will be an even simpler simplified view of G, because you're making more things, because H contains n. You're making, in general, more things in the group G. You're insisting that they be equivalent to the identity. Okay, so you're simplifying even more. So the factor group G mod H will be quite small compared to G mod n. Okay. So G mod n will be a less simplified view of G compared to G mod H. But so how do we make the less simplified thing equivalent to the extra simplified thing? We have to simplify the less simplified thing a little bit more. And we do that by quotienting out by a normal subgroup of that, which will be H mod n. So the third isomorphism theorem sets up the maps, sets up the isomorphic, the bijective map between these two sets, and proves that it is an isomorphism. So you'll have lots of little proofs of the conditions, proving that the map is well defined, proving that the map is injective, proving that it's surjective, and all these little justifications you have will all be justified by appealing to the fact that n and h are normal in G and that n is contained in H. Okay. And it's quite appealing because you can kind of think of this as cancellations and simplifications, like, because the structure of what's going on here is the same. Like if you were talking about integers and you had a fraction a over b divided by c over b, that of course would be equal to the fraction a over c. Yeah. The b's cancel out. So you're dividing the top of the fraction by b, and you're dividing the bottom of the fraction by b. You're doing the same thing to the top and bottom, so those two operations can be cancelled out, and this fraction, or this fraction of fractions, is just equal to this fraction. If these are numbers, a, b, c, these are numbers, and b and c are not zero, so you're not doing anything funny with zero. Okay, these are certainly not numbers. This is certainly not a division of numbers. It's something completely different. These are groups. This is a factor group operation. But nevertheless, the structure and behavior of combined doing successive operations, taking the factor group of factor groups, as long as they're all lined up and they're of the right form, and so this thing here is a normal subgroup of G mod n. So that fact was proved in the previous correspondence theorem, that H mod n is a normal subgroup of G mod n. So this is a valid factor group construction, and naively you think, oh well, you're dividing by n there, you're dividing by n there, those two operations cancel out, so you're just left with G divided by H. Okay, that's the normal kind of reason you'd want to be very suspicious of, because you're treating them as just normal numbers in division. But that intuition or that naive expectation does carry through. So that's really, really nice. It justifies the use of this kind of fractional type notation for these objects. Even though these aren't numbers, we aren't forming fractions of numbers, but it's a sensible choice to use this kind of notation because it does respect the kind of rules, the familiar rules we've built up about forming fractions. Okay. So that's the third isomorphism. I won't take you through all the nitty-gritty details. None of the individual details are particularly hard. It's just you have to set up an isomorphism here, so you have to define what the map is between these objects. You have to show that it's well defined, it's injective, and it's surjective, and it satisfies the homomorphism property. Okay, all those individual justifications you need all come from the fact that n and h are normal subgroups of G, and n is contained in H. So I'm relying on previous results in the correspondence. Okay. So any questions about it? So we have hopped over a lot of those technical details. We kind of saw most of them in the discussion of the first lesson. Okay, so next I'd like to start looking at some of the exercises at the end of that chapter. Just so we can start making things a little bit more concrete. Because in all that discussion there, we were talking completely in the abstract algebra sense. We haven't named any of our groups as being particular concrete groups. We were just treating them as general groups and so on. So if we come back down to ground a little bit and start looking at some exercises, and these chiefly concern actual concrete groups. So these are the exercises on page 185. Yeah. So the first of these, do feel free to ask any questions about this. So the first of these is kind of a discovery. Well, getting you to meet this interesting result. So yeah, here we're looking at this function det, which is the determinant. So we're taking this from GL2R to R star. So this here is the group of 2 by 2 real matrices under multiplication of matrices. Under multiplication, and this is the group of non-zero reals under multiplication as well. Okay, but here on the right, we mean multiplication of real numbers. Here on the left, we mean multiplication of matrices. And this first exercise just says that prove that det is a homomorphism. So what's the homomorphism property here? The homomorphism property here says that if you take det of a product of matrices, take the determinant of a product of matrices, it is the product, under multiplication of real numbers, the product of the individual determinants. I.e., det of a product of matrices is the product of the determinants. So you notice this product here is taking place in GL2, product of these two matrices. This product here, product of the two determinants, well, the determinants are just real numbers, and you're multiplying together the real numbers. So that is exactly the homomorphism. Of course, you're very familiar with that property already. That was central to one of your coursework problems in the linear algebra last year, Stephen, remember? And it's something that we use at the drop of a hat when we're doing matrix algebra as well. Now you can prove it on the level of 2 by 2 matrices without too much trouble. So you can let A, so you'd have to be quite general. So you've got a matrix A, you've got a matrix B, E, F, G, H. Okay, the determinant of A, of course, is AD minus CB. The determinant of B is EH minus GF. Familiar with that. And the product matrix AB. So doing that quickly, it's AE plus EG, CE plus GD. Then in the right-hand column, you've got AF plus BH, and then CF plus EH. So the determinant of AB will be AE plus BG times CF plus DH minus CE plus GD times AF plus GH. And the product of the two determinants, determinant of A times the determinant of B, is, we've already got determinant of A is AD minus CB, and determinant of B is EH minus GF. So in order to prove this, then, you just have to verify that these two expressions are the same. Okay, it looks hopeful. Each of the expressions is just some big mixture of A, B, C, D, E, F, G, H. So hopefully they're the same mixture. Now, when you multiply out this bracket here, you get a sum of 4 terms. Each term has 4 variables in it. So AD times EH minus CB times EH. So you get 4 of those terms. Each of them have 4 variables in it. But when you expand out this line, well, you get 4 terms here, each with 4 variables, and you get 4 terms here, each with 4 variables. So you get 8 terms in total. So some of these ones here are going to cancel out simply. You're going to get positive and negative versions of some terms here. The ones that don't cancel out will be exactly the ones that are generated from here. So let's see some of the ones that cancel out in the determinant of A times B. So for instance, here you've got AE times CF. But when you look here, you've got minus CEAF. So AECF, AECF. So you got a positive term here and a negative term here, which cancel out with each other. Well, one of the ones that will not cancel out is the AEDH. You've got a product up here, AEDH. There's no negative version of that that's going to cancel out of it. But AEDH is exactly something you get down here. Yeah, this bit times this bit here, AEDH. Okay. So by just simple inspection, these two are the same. These two are the same by inspection. Or just multiply them all out, and you'll see that they simplify down to be the same. So that proves that the determinant is a homomorphism, at least on GL2 to R. In fact, det from GL from any size of square matrices to the same, the group of multiplicative real numbers, this will also be a homomorphism. Well, of course, you don't want to prove it like this for a general size. If you're talking about 10 by 10 matrices, you don't want to start actually writing out, expanding out the full determinant. So to make a remark here, a very useful formula, and it's maybe one you haven't seen up to now, a very useful formula defining the determinant which allows you to prove a lot of these properties, allows one to prove a lot of determinant properties. And one reason you might have seen it before up to now is that it does use the idea of permutations, but we've fully met permutations here. And we know that. So if A is an n by n matrix, remember we only defined the determinant for square matrices, then the determinant of A can be defined as you're adding up, you're summing over every permutation in Sn. So we're making use of all the permutations in the symmetric group Sn. We're introducing, so what is sign? The SGN is just an abbreviation for the sign of a permutation. SGN of a permutation is +1 if the permutation is even, -1 if the permutation is odd. It's the sign of a permutation. So we attach a positive sign to the even permutations and a negative sign to the negative permutations. And then we're taking the product. Basically what we're doing is we're taking all possible products of entries from the matrix where you're taking one entry from each row. One entry from each row and never taking more than one entry from each column. And the way we do that is we choose the thing in position in the ith row and the sigma ith column. So remember, sigma is a permutation, so it's a bijective mapping from the labels 1 to n to the labels 1 to n. So you can think of that as a bijective mapping from the rows of the matrix to the columns of the matrix. And so you're selecting the entry from the ith row and the sigma ith column, and you're multiplying them all together across all the rows. And you're summing over all positive products like that. And some of them have a positive sign, some of them have a negative sign. So this is the same determinant that you've defined in other ways through cofactor expansions and so on. And you're familiar with the idea. I mean, you can even see it here. When you expand out the 2 by 2 determinant, you get a mixed, you see here we've taken the first entry from the first row, the second entry from the second row, and we attach a certain sign to it, positive or negative. Next product is we take the second entry from the first row and the first entry from the second row, and that gets a minus. And if you expand out a general 3 by 3 determinant as well, you see you get it as a bunch of terms. Each term is a product of 3 things, one thing from each row and column. And there's a positive or negative sign attached to it. And if you actually examine what comes out, it's actually exactly this expression here. Okay? And this expression works in general. You see the general recipe now, and that can be applied in general to any size of matrix. So in particular, this multiplicative property of the determinant, that the determinant of A times B is equal to the determinant of A times the determinant of B, that kind of thing can be proved quite nicely using this form. The factorization results about factoring a determinant, taking an entry, factoring an entry out of each row of the matrix and bringing that factor outside the determinant, that can be proved quite easily here. The result about two rows being the same, then the determinant is 0, that comes out. In fact, basically all those properties of determinants, I think, can be proved quite nicely using this definition of the determinant. Okay. Any questions about that? The second question sticks with matrices and real numbers. And you see there on page 186, it gives you a lot of candidate homomorphisms. So it gives you a lot of mappings from sets from either numbers to matrices or matrices to numbers, and asks you for each one, is it a homomorphism? If it is a homomorphism, what is the kernel? So we could look at some of these. And so the first one, we've got a phi from the non-zero real numbers to GL2 R, and you send the number A to the matrix 1A 0 0. So first of all, we just recognize that it is as claimed. It is as claimed a valid map from R star to GL2. Because if you have a non-zero number A here, what's the determinant of this matrix? The determinant of that matrix there is simply A. Yeah, it's 1 times A minus 0 times 0. So if A is non-zero, because it's coming from R star, then the determinant is non-zero. So it is an element of GL2R. GL2R just consists of the matrices with 0 determinant, i.e. the invertible matrices. Because the group operation here is multiplication of matrices, so we need every matrix. So is it a homomorphism? Is phi a homomorphism? So the question is, that becomes the question, for every A and B in R star, is phi of A times B equal to phi of A times phi of B? Question. Is that true? Well, just apply the definition of phi, see what it is. And so in other words, we're asking phi of AB, that's the matrix 1, AB, 0, 0. Is that the same as phi of A, which is this matrix, times phi of B? Question. Maybe it's always the same. Maybe those two are always the same. Maybe they're different. Notice that the product here is going on in R star, remember? This product here is going on in GL2. We're applying phi to that. So we're just applying this rule to the product AB. So we got this matrix here, and so equal to that. Is that true? Yeah. Yeah, just using the rules of matrix multiplication. Yeah, you can see indeed where when you multiply those two, you do indeed get that. So we can answer yes to the question. Yes. Simply true by the definition of matrix multiplication. Okay. So it is a homomorphism. What does the kernel of it look like? If it is a homomorphism, we can form its kernel. So, answers for the kernel. Yeah, remember what the kernel was. The kernel was the set of everything in the domain that got sent to the identity. Phi of x equals the identity. That's the general group theory type definition of it. Well, let's unravel that definition. What is phi of x? Phi of x is this matrix here. And what is the identity element in GL2? Well, it's the thing we call the identity matrix. Okay, this is a group under matrix multiplication. So the identity is the identity. So which x's solve this? This equation. Just x equals 1. Yeah. So it's just a singleton set x equals 1. And of course, 1 is the identity element in the domain group R star. Group of real non-zero real numbers under multiplication. 1 is the identity element. So can we conclude something about the mapping phi from that? Seeing that the kernel consists of the identity element. We discussed that in the last section. That tells us that phi is injective. Remember, the kernel consists of everything in the domain that the mapping collapses down onto the identity element in the codomain. So if the function is not injective, if in general it does collapse different elements down onto the same element, it will be collapsing different elements down onto the identity element. Okay. You can get that phi considering the group operation and inverses and so on. So in particular, if we see that the kernel just consists of the identity from the domain, as it has to contain the identity, but if the identity from the domain is all that's there, that means it's not collapsing anything non-trivial down onto the identity element. Well, then it won't be doing any collapsing of distinct elements down onto the same element. So it will be injected. So that implies that phi is injected. That was by remarks we made earlier when we introduced the kernel. So that gives you an idea. I mean, there's a load of other maps to get thinking about there to going either from R to GL2 or GL2 to R or M2 to R. So notice in those exercises when if he talks about the group R star, he's meaning the group of non-zero real numbers under multiplication. But if he just mentions R, he's talking about the group of all real numbers under addition. Yeah. And GL2R is the group of invertible matrices under multiplication of matrices. M2R is simply the set of all 2 by 2 matrices under addition of matrices. Yeah, those were the conventions. This was multiplication of matrices. This was addition of matrices. So some of those maps phi will be homomorphisms. Some of them won't. So you want to be able to assess each of them and decide. You do it much the same way as you did the first one, and then examine the homomorphism of any that you think are, or examine the kernel of any that you think are homomorphisms. Okay, we'll end it there for this morning. We can maybe fit in a few more of these exercises on Friday as well. I'd encourage you to try some of the other ones in the meantime. I think all of them up as far as 12 and 13 are kind of strict, are nice. And then they get a little bit harder about the factor constructions and that between 14 or 13 and 19. Okay. We could have a look at some more of those on Friday. And in addition, any queries you might have about permutations or anything really needed in support of the coursework, I'd encourage you to raise those issues on Friday as well.